sorry about that. Next up, we would like all of the acceptable Lewis structures for C2H2Cl2. What are these structures and which of them are polar or non-polar? Okay, and so with organic compounds that are in the format of C, so CnH, some function of N, and then you have a halogen. In order to figure out what it should look like, let's go about just replacing all of those halogens instead with hydrogens. And so in the case of C2H2Cl2, let's just think about what C2H4 would look like. And so C2H4, we know is going to be an alkene because it's following the general formula of CnH2n. And so we can expect this for C2H4. And so now, because we have two halogens instead of the two hydrogens, so instead of the four hydrogens, let's just replace two hydrogens with the halogen that we have, so Cl instead. And if you'd like to just double check that this is all correct, we can count our valence electrons. And we know that we'll have 2 plus 8 plus 14. And that is going to give us 24 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Our valence electrons are all taken care of. Our formal charge on the carbon, we're going to have 4 minus 4, giving us 0. On the hydrogen, we're going to have 1 minus 1, giving us 0. And on the chlorine, we're going to have 7 minus 6 minus 1, giving us 0, 2. So clearly this structure is good to go. And so now that we have this structure, let's see if anything can be moved around. We know that it does not have to be these two chlorines on this one side, and so it can also be the structure looking like this. Let's just switch these two, right? And note this isn't the only other configuration other than this one. We can again switch two. And so now that we switched these two, instead of doing that, let's switch these two. And so we will have this structure. And so we haven't changed any of the formal charges, we haven't changed any of the valence electrons, we've just moved where the chlorines are. And so these are the three acceptable Lewis structures because all of them check out in terms of the counting. And so now let's go about drawing them. Both of these carbons are going to be sp3 hybridized, right? And so if we draw out each of their structures, it's going to be trigonal planar. And so we will have two trigonal planar looking carbons. And I know it's tempting to say, of course, what about like the case where we have two Cl's here and the H's here? We technically consider that the same thing as this at this level. And same thing, if you reflected this and had the two Cl's here instead, we'd also consider it the same as this one. And similarly, if we had the two Cl's here instead of here, we'd consider it the same. So these are our three structures that we can work with. And so now that we've drawn out the molecular geometry, let's see if the dipoles will cancel to determine which ones are polar and non-polar. So in this case, we have this dipole pointing this way, this dipole pointing this way, this dipole pointing this way, and this dipole pointing this way. Again, chlorine is the more electronegative. Between carbon and hydrogen, carbon is the more electronegative. And then lastly, we will have okay, and so now we need to, let's actually draw the chlorine dipoles in a different color. And that's just because the magnitude of the dipole, which is determined by the difference in electronegativity between the carbon and the chlorine and the carbon and the hydrogen, they're going to be different. because the difference in electronegativity between carbon and chlorine compared to hydrogen and carbon is different. And so, okay, and so let's see if anything will cancel out exactly as it should. Okay, so in this case, we see that these two dipoles are equal and they're opposite in direction. So these two will cancel. Similarly here, they're equal and opposite in direction. So these two will also cancel. Here we see nothing is equal to the other one. And so these two, their angular components will cancel each other out indeed, but it'll still leave you with the same, component facing up, because that one hasn't canceled out. The same thing here, the two angular components will cancel out, but the one pointing up itself will not cancel. These two vectors obviously cannot cancel out. Sorry, these two dipoles obviously cannot cancel out, and so we'll have a non-zero dipole moment. And we know that that means that this molecule is going to be polar. Here we've seen that they do cancel, so this one is non-polar. And lastly, let's check on this one. It's going to be similar to what we had in this case, where yes, the angular components here will cancel, but it will leave you with this vector pointing to the right. Same thing here, angular components will cancel, but it will still leave you with this vector pointing to the right. And so these two obviously can't cancel, and you'll have a non-zero dipole moment. Let's just write out all of their net dipole moments. And so obviously that means that this one will be polar. And just so you know, this one has the name of, it's called cis. And that's strictly because these two are across from each other. This one is called trans. And that's strictly because these two are on the same side of the bond. If you consider this other side and this other side, opposite side, cis, same side, trans. And so as our final answer, we will have the trans molecule as polar, the cis molecule as non-polar, and this last one as polar.